see, and then no. Wait a second. Stop recording. Okay, so it's a pleasure to welcome Toke Meier Carlsen, who will speak about sister rigidity of topological dynamical systems. So please, Toke, go ahead.
Thank you very much for the opportunity to give a talk at this seminar. I hope there's not too much background noise, but there's a major construction work going on right outside my window. So maybe you'll hear a bit of the noise. So before I begin, let me post a link to a copy of the slides in the chat, so you can download the slides and follow along if you like. Okay. So as you can see, I'm going to talk about what is sometimes called C-style rigidity of topological dynamical systems. So there is a long tradition for constructing C-style algebras from dynamical systems. And the main motivations for doing this are to get new examples of C-style algebras, which can be studied via dynamical systems, and to use operator algebra theory to study dynamical systems. When one constructs a C-style algebra from a dynamical system, then it's natural to ask how much information about the dynamical system can be obtained from the C-style algebra. So one might also ask if it's possible to recover the dynamical systems from the C-style algebra. So what we here call C-style rigidity of dynamical systems is the principle that dynamical systems can be recovered up to suitable notion of equivalence from C-style algebraic data associated to them. So a good example of this principle comes from a Cantor minimal system. So we call that a Cantor minimal system consists of a totally disconnected compact metric space with no isolated points and a homomorphism such that there's no non-trivial closed invariant subspace. The latter condition, the condition that there's no non-trivial closed invariant subspace, is equivalent to the condition that this orbit here is dense for any point in the space. Two Cantor minimal systems are said to be strong orbit equivalent if there's a homomorphism H from X to Y, and two maps M and N from X to the set of integers, such that these two conditions holds for any point in the space. And such that the two maps in M and N have at most one point of discontinuity each. So why is this called strong orbit equivalent? Well, if you have any homomorphism from X to Y, then it will map an orbit like this to an orbit precisely when there are maps M and N from X to the set of integers satisfying these two relations here. And then if these maps can be chosen to be to have at most one point of discontinuity, then we say that the equivalence is a strong orbit equivalence. So Giordano, Putnam, and Skau showed in 1995 that for two Cantor minimal systems, the corresponding C-star cross products are isomorphic if and only if the K0 groups of the cross products are isomorphic by an order-preserving isomorphism that maps the class of the unit to the class of the unit. And this happens if and only if the two Cantor minimal systems are strong orbit equivalent. So I've written George Eliot's name here, and that's because the equivalence of 1 and 2 actually follows from a classification result that George proved in 93. But Giordano, Putnam, Skau, they proved this theorem here without using that classification result. What they proved is that if the two Cantor minimal systems are strong orbit equivalents, then the C-star cross products are isomorphic, and that one implies two. That follows from general theory of K-theory, and then Giordano, Putnam, and Skau proved that two here, that if we have an order preserving isomorphism of the K groups that sends the class of the unit to the class of units, then the Cantor minimal systems are strong orbit equivalents. So that gives that 2 implying 3. Yeah.
May I ask something? So the result of Elliott that you refer to is the classification of almost finite sister algebras, or?
No, it's I forgot exactly which one it is. I guess I think these are AT algebras. That's.
Uh-huh.
Yeah.
Okay.
Yeah. So this another way of formulating the theorem is that it's possible to recover a Cantor minimal system up to strong orbit equivalence from its C-star cross product. So that's an example of what I call C-star rigidity. So this theorem is a bit unusual because you can recover the dynamical systems just from a C-star algebra. As we'll see in a minute, usually we'll require more information than just the C-star algebra. It can be either a sub-algebra, or it can be an action of the C-star algebra.
One other question. I don't exactly recall the precise statement, but I understand that there is a result in LP operator algebras, P, not 2, that an isomorphism between group LP algebras implies an isomorphism between the groups.
Okay.
And so I wonder if, I mean, there might be more rigidity results of that sort, not just for group algebras, but for these groupoid algebras.
Yeah. I don't know. I hardly know anything about LP algebras, so so I can't say so much. But I guess maybe it's the case that the LP algebras are somehow a finer invariant of the dynamical systems. That the I mean, the property of C-star algebras is that I guess they are more easily isomorphic than other kind of systems. So it's I guess it's a bit rare to see this kind of C-star rigidity. Yeah, but it happens in some cases. Okay, so as I said, often you will require more than just the C-star algebra to recover a dynamical system. So an example of this also comes from Giordano, Putnam, and Skau. So they were able to also recover Cantor minimal systems up to continuous orbit equivalent. So two Cantor minimal systems are continuously orbit equivalent if there's a homomorphism from X to Y, and continuous maps M and N from X to the set of integers satisfying these two conditions we saw in connection with strong orbit equivalence here. But the difference here between strong orbit equivalence and continuous orbit equivalence is that now we require the two maps M and N to be continuous. Before we allowed them to have a point of discontinuity. Then there's also another notion that is relevant here. That's the notion of flip conjugacy. So we say that the two systems are flip conjugate if there's a homomorphism between them, such that either this condition holds for all x or this condition holds for all x and x. So the first condition says that H is a conjugacy, and the second condition says that it's an anti-conjugacy. So flip conjugacy just means that the systems are either conjugate or anti-conjugate. And Giordano, Putnam, and Skau then used a result of Mike Boyle to show that the cross product of two Cantor systems are isomorphic by an isomorphism that maps C of x onto C of y, if and only if the Cantor minimum systems are continuous orbit equivalent, and if and only if the systems are flip conjugate. So the result of Boyle gives you that that 2 implies 3, and it's fairly straightforward to check that 3 implies 1. So what Giordano, Putnam, and Skau did was to show that we have that 1 implies 2. So shortly after this result, Yu and Tomiyama showed that this last theorem here can be, and its proof can be generalized to so-called topological transitive dynamical systems on compact matrix spaces. So a topological dynamical system is topological transitive if there's at least one point whose orbit is dense. So in a Cantor minimum system, every orbit is dense. So a Cantor minimum system is an example of a topological transitive system. And the result of Mike Boyle that Giordano, Putnam, and Skau used, it actually holds for topological free dynamical systems on compact metric spaces. And what Tomiyama did was to notice that Giordano, Putnam, and Skau's proof can be extended to the topological free setting here. No, sorry, to the topological transitive setting. Yeah. So shortly after this, there was another generalization of these kind of results. So Mike Boyle and Yu Tomiyama got together and then generalized this result to what is called topological free dynamical systems. So a topological dynamical system is said to be topological free if the set of non-periodic points is dense in dense. And then Boyle or Tomiyama showed that if we have two topological free dynamical systems on compact Hausdorff spaces, then the cross product Cyst algebras are isomorphic by an isomorphism that maps Cx onto Cy. If and only if these two systems are continuous orbit equivalent, and if and only if there's decompositions of x and of y, such that the restriction of phi to x1 is conjugate to the restriction of psi to y1, and the restriction of phi to x2 is anti-conjugate to the restriction of psi to y2. So, yeah?
Could you explain the logical relation between the hypotheses of the previous theorem and this one. So it's not clear to me whether the existence of an X whose orbit is dense in X and the fact that the assumption that the orbits that are topologically free are dense, whether there is a logical implication between the two. Or...
No, it's not obvious. But if the space is infinite, then if a system is topological transitive, then it's also topological free. But you need it to be infinite, because in a finite space, you will have every point will be periodic. So, but in the infinite case, topological transitive implies topological free. And moreover, if the systems are topological transitive, so there is a dense orbit, then when you make such a decomposition, so decompositions here, I think I forgot to say that, but x1 and x2 and y1 and x and y2, they have to be invariant. So if the systems are topological free, then these two decompositions, they are trivial. I mean, either x1 is empty or x2 is empty, and the same with y1 and y2. So in the topological transitive case, then this theorem here is exactly the theorem here. So this is really a generalization of the previous result. Okay, so I have one more result in this setting here. So I showed together with Ruiz, Sims, and Tomford in a paper that's just been published, a partial generalization of the previous result, when we showed that if we have two second countable Hausdorff spaces and two homomorphisms, one on each space, then the cross product Cyst algebras are isomorphic by an isomorphism that maps C of X onto C of Y. Exactly when we can make a decomposition as in the previous result here. So what is new here is that there's no longer any conditions on the maps here. They just have to be homomorphisms, but then we lose the condition about the systems being continuously orbit equivalent. And what happens here is, instead of two, we actually have a condition that says that the transformation group points are isomorphic. And in the topological free setting, the transformation group points are isomorphic exactly when the systems are continuously orbit equivalent, but that doesn't hold for non-topological free systems. Okay, so let us now leave this setting of classical dynamical systems and move on to Cyst algebraic dynamical system. So two actions of a locally compact group on Cyst algebras are said to be conjugate if there's an isomorphism between the Cyst algebras that intertwines the two actions. And the actions are outer conjugate if one action is conjugate to an action B prime on B, such that there's a strictly continuous unitary map from the group to the multiplier algebra of B, satisfying this co-cycle condition, such that B prime is the composition of beta prime is the composition of beta with adjunction of this unitary action. Recently, Kalchetsky, Omland, and Quick used an old result by Gerd Petersen to show that two cross products of locally compact group on arbitrary Cyst algebras are isomorphic by an isomorphism that maps A onto B and intertwines the dual coactions alpha hat and beta hat precisely when the two C-star dynamical systems are out of conjugate. So this is an example of a rigidity result about C-star dynamical systems, and in this case we can recover the two or a C-star dynamical system up to outer conjugacy by the cross products together with the canonical copy of A and B together with the dual coactions. But in some cases, this requirement that the isomorphism between the cross product maps A onto B is not necessary. So for instance, it follows from, sorry, yeah.
One little question. These dual coactions, you mean the dual coactions on the cross product?
Yeah, yeah.
Okay.
Yeah, thank you. So it follows from Imai Takesaki duality for that two C-star dynamical systems of a locally compact group are isomorphic by an isomorphism that intertwines the dual coactions. If and only if these two tensor product here, the A tensor with the compact operators on L2 of the group, and B tensor the compact operators are also on L2 of the group, with the tensor product of the action alpha with the left regular representation of on L2 is conjugate to the to beta tensor the left regular representation. And that's simply because if you take the cross product of the dual coactions, then you get something which is isomorphic to this tensor product here. So in that way, you can recover a C-star algebra up to stable isomorphism from its cross product together with the dual coaction. So here we relax the condition on of the isomorphism between the cross product because we don't require that A is mapped to B, and the price we pay is that we only recover the C-star algebraic dynamical system up to stable isomorphism.
Okay, so in the previous theorem, I mean, say you want to prove 1 implies 2, right?
Yeah.
Then you take the cross product with G hat, you obtain the stabilization of A and B, that they are isomorphic, and the fact that the isomorphism maps A to B, you use these two things to conclude, I mean, to get some isomorphism between A and B. I mean,
yeah, but it requires some work. But
yeah, that's the idea.
Yeah. I suppose that's exactly the idea. Yeah. Yeah.
Okay. Thank you.
Okay. So Karachevsky, Omland, and Quick also proved that if we assume that the group is G is discrete, and we then have an action alpha of G on Cyst algebra A and an action beta of G on Cyst algebra B, then the cross product are isomorphic by an isomorphism that intertwines the dual coactions precisely when the dynamical systems are out of conjugate. So that's a strengthening of this result here, because in this case, when the group is discrete, then you don't have to ask that the isomorphism takes A onto B. Yeah, this requires some clever tricks to get rid of this condition here. Karachevsky, Omland, and Quick also prove that if we go back to the classical setting, so we have a locally compact group acting on locally compact Hausdorff spaces, then the two actions are conjugate if and only if the corresponding cross products are isomorphic by an isomorphism that intertwines the dual coactions. Okay, so there were some examples of C-star rigidity. All of these results are about group actions on either topological spaces or Cyst algebras, and the Cyst algebra that we're working with are the cross products. But there are also rigidity results for Cyst algebras constructed from irreversible dynamical systems. And the nicest example of this is in the setting of conjugate algebra. So I will just for now restrict to conjugate algebras. Some of the results can be generalized to more general settings, but I think the setting of conjugate algebras is very nice. So let's stick to that. So as you may know, the conjugate algebras can be considered as Cyst algebras associated with topological Markov shift. So let me just briefly recall what I mean by a topological Markov shift. So I start out with an n by n matrix, with n by n matrix with entrance in 0, 1, and I assume it has no zeros and no 0 columns. And then we let XA be the set of all sequences for which the entrance of the matrix A corresponding to two consecutive elements of the sequence is always equal to 1. And then we take this set of sequences and we equip it with the product topology. Then we get a totally disconnected compact Hausdorff space. And then we define the shift operator like this. So we just take a sequence and then forget about the first element of the sequence and shift every other sequence, every other element one to the left.
So sorry, if I think of the matrix as being associated to a graph, then this will be the space of all infinite paths in the graph.
Exactly.
Right? Okay.
Exactly. Yeah. And then this shift map here is a surjective local homomorphism, but it's not a homomorphism, because I mean we are throwing away the first element of the sequence, and we can have two sequences which are equal except at the first element. So it's not the shift map is not necessarily injective, and therefore not necessarily a homomorphism. But this is what I would call an irreversible dynamical system, topological dynamical system, and it's this particular type of dynamical system is sometimes called a topological Markov shift. It's an example of what is also called a shift of finite type. And in fact, every shift of finite type is isomorphic to one of these topological Markov shifts. Okay. So we say that two one-sided topological Markov shifts, I call them these one-sided because our sequences here are one-sided. They are indexed by the non-negative integers. Later on, we will talk about two-sided sequences. But for now, we look at one-sided sequences. So we say that the two one-sided topological Markov shifts are continuously orbit equivalent if there's the homomorphism from XA to XB and continuous maps K and L from XA to the set of non-negative integers and K prime and L prime from XB to the set of non-negative integers, satisfying this condition for every X in XA and this condition here for every X prime in XB. So at first this might seem like a bit strange definition, but if you take any bijection between XA and XB, it will map orbits to orbits exactly when there exist maps K, L, K prime, and L prime, such that these two conditions are satisfied. So that is what we will call orbit equivalence, and then continuous orbit equivalence is when H is a homomorphism and the maps K, L, K prime, and L prime are continuous. Okay. I want to introduce another notion of equivalence of one-sided topological Markov shift. So we say that two one-sided topological Markov shifts are eventually conjugate if they are continuously orbit equivalent in a way such that we can choose the L to be K plus 1 and the L prime to be K prime plus 1. So here, instead of L, I've written Kx of plus 1, and instead of L prime, we have K prime X prime plus 1. So eventually conjugacy is stronger than continuous orbit equivalence, and I haven't written down what conjugacy is, but conjugacy is just a case where we have eventually conjugacy and where K and K prime are constantly equal to 0. But in connection with discrete algebras, continuous orbit equivalence and eventual conjugacy will be more relevant than conjugacy. Then a little bit of notation. So OA will be the discrete algebra of A, and then DA will be the C-star subalgebra of OA generated by elements of this form here. So the SI1 and SIK, they are the canonical generators of OA, and then we look at elements of this form here. And look at the C-star subalgebra generated by this, and this is what we denote by DA. This is, in fact, a commutative C-star algebra, and its spectrum is this space X of A here. So DA is isomorphic to the C-star algebra of continuous functions on XA. And the last ingredient before I state the next result is the gauge action of OA. So this is an action by the unit circle on OA that is given by this condition here, that it scales every generator by an element of the unit circle. Good. We then have that the two one-sided topological Markov shifts are continuously orbit equivalent, exactly when there is an isomorphism between the corresponding conjugate algebra that maps dA onto dB. And we have that two one-sided topological Markov shifts are eventually conjugate, exactly when there's an isomorphism between the conjugate algebras that maps dA onto dB and intertwines the gauge actions. So these two results were first proven by Kinko Matsumoto for irreducible topological Markov shift, and then for arbitrary topological Markov shift by Søren Eilers, Ortega, Restov, and myself in this case here, and then by James Rout and myself in the second case.
One little question. So this is, I mean, there are these conjectures by Hartrat about gauge. So how does this relate to that? The sister algebra version, I mean, of his conjecture.
So these two results, they also hold for Levy path algebras. But then instead of the gauge action, you talk about the grading. Mm-hmm. But we could add here that there is an isomorphism between the Levy path algebra that maps what corresponds to dA onto dB, and down here that there's an isomorphism between the Levy path algebras that maps dA onto dB and is graded.
So the key is that in Hartrat's conjecture, he doesn't ask for the diagonal to be reserved.
Yeah. And then it's much more difficult because so I will get back to this later, how to prove this, but this is proven by using groupoids. And to use that, it's essential that you have this condition here that dA is mapped onto dB. Without this condition, you cannot use this machinery of groupoid. You have to do something else. But there is actually, so there is a result, an old result by Kishimoto and Bradley that in the, so that's for primitive matrices characterized when you have a gauge invariant isomorphism between the conjugate algebras in terms of the topological Markov shifts. But it's really a C-star algebraic proof, and I don't know if you can do something similar in the algebraic setting, and it also seems difficult to generalize to the general case where you don't have primitive matrices.
But I mean, Hartrat's conjecture has I mean, there are two parts, one for the Levy path algebras and one for the sister path algebras. So you're saying that in the primitive case, Hartrat's conjecture for the sister algebras does hold.
Yeah.
Okay.
I believe that's the case. I mean, yeah. Maybe I'm missing something, but I think that's correct. Yeah.
Okay.
Okay. So these are results about the one-sided topological Markov shift. We also have similar results about two-sided topological Markov shift. So again, I start with an n by n matrix with entrance in 0, 1, no 0 rows and no 0 columns. And then the two-sided topological Markov shift is defined in the same way as the one-sided Markov shift, with the exception that now we're looking at bi-infinite sequences. So that's sequences indexed by the set of integers instead of the set of non-negative integers. But otherwise, the condition is the same. And we also equip this space with the product topology. And we can also define the shift map here. And the space is again, totally disconnected compact Hausdorff space. But this time here, the map is not only a local homomorphism, exactly a homomorphism, because now we are not throwing away any information when we shift a sequence. We're just changing the indices. So in some sense, these are more, they are nicer dynamical systems. These are classical topological dynamical systems.
Sorry, is there a relation? I mean, in the if you have when you have a conjugated algebra, you can view it as a cross product of the part of, say, degree 0, the part fixed by the gauge action, with a partial cross product. And then when you stabilize, you get a cross product in the usual sense. So is there a relation between that and using two-sided topological Markov shift as opposed to one-sided?
Well, I guess there's a relation with it, but it's not obvious, and I don't understand it very well.
So the cross product sister algebra in the two-sided topological Markov shift case is not the stabilization of the other one or something.
No, they are quite different. So usually, if you take the cross product of the two-sided Markov shift, then you get a Cyst algebra which is non-simple, because every subshift will give you an ideal. But the conjugate algebras, of course, are often simple Cyst algebras. So they are quite different. And I guess it's a bit surprising, at least it was to me when I first saw the definition of the conjugate algebra. It's really using the one-sided shift base, the Markov shift, but it turns out that it also encodes a lot of information about the two-sided shift base, as we'll see now. So just a little bit of notation. So there's the notion of flow equivalence. So we say that two-sided topological Markov shift are flow equivalent if there's a homomorphism between what is called the suspensions that match flow lines onto flow lines in an orientation preserving way. So here tilde is the equivalent relation defined on the product of the two-sided shift base with R, generated by the relation that sigma bar A of x comma t is related to x comma t plus 1. And a flow line is then a set of the form x comma t, where x is fixed and t runs through all of R. So this notion here, flow equivalence, it's a notion that's very natural in dynamics. So it's a way of taking a discrete topological dynamical system, making it into a dynamical system where a continuous dynamical system where R is acting instead of Z. And we also have the notion of conjugacy, So that's the case when you have a homomorphism between the shift bases that intertwines the two shift maps here. And then finally, we let K denote the Cyst algebra of compact operators, and C here is then the subalgebra of K generated by the diagonal operators. And then we have the two topological Markov shifts are flow equivalent exactly when there is a isomorphism between the stabilized concrete algebras that maps dA tensor C onto dB tensor C. And similar, we have the two topological Markov shifts conjugate exactly when there's an isomorphism between the stabilized concrete algebras that maps dA tensor C onto dB tensor C and intertwines the stabilized gauge actions.
Mm-hmm.
So this says here that you can recover a two-sided topological Markov shift up to either flow equivalence or a two-sided conjugacy from its stabilized concrete algebra together with this subalgebra and in this case also the stabilized gauge action. So in both cases, Kunz and Krieger, they showed that 1 implies 2, both in here and here. And then that 2 implies 1 here was proven by Matsumoto and Matsui in the irreducible case, and then by Eilers, Ortega, Restov, and myself in the general case. And here 2 implies 1 was proven by James Stroud and myself. Okay, so all these results here about topological Markov shift and conjugate algebras, and also the results I told you about the classical topological dynamical systems and their cross product Cyst algebras, they can be proven with the help of groupoids. So I will end by briefly telling you about this. So I don't know if maybe you're all familiar with groupoids, but here's a crash course in Étale groupoids. So a groupoid is a small category in which every morphism has an inverse. So you can also think of it as a generalization of both a group and of a space. And a topological groupoid is then a groupoid with a topology such that composition and the inverse operator they are continuous. And a topological groupoid is called Étale if the range map or equivalent to the source map is a local homomorphism. So here I use the tradition of instead of calling it the codomain, I call it the range, and instead of calling it the domain, I call it the source. So this is often the case when you use groupoids in connection with Cyst algebras, that you use range and source instead of codomain and domain. So a second canonical locally compact Hausdorff-Étale groupoid is what is called topological principle if it is effective, and that means that the interior of this set here is the set of identity isomorphisms. So here we look at all the morphisms where the range is equal to the source, and here for every G0 is the set of objects, and for every object in a category you have an identity morphism. So if the interior of this set here is just a set of identity morphisms, then the groupoid is effective, which is the same as topological principle in this setting here. And in 2008, Jean Renaud, who is the father of the theory of C-star algebras of topological groupoids, proved by building on work by Alex Kumjian that two topological principles, second countable locally compact Hausdorff et al. Groupoids, they are isomorphic by in a topological sense, or by an isomorphism that is also a homomorphism, precisely when there is an isomorphism between the reduced C-star algebra of the two groupoids that maps C0 of the unit space onto C0 of the other unit space. So the C0 of the unit space is an abelian subalgebra of the reduced C-star algebra of the groupoid. So this is very similar to a lot of the previous results, and in fact, this result here can be used to prove several of the previous results.
So this condition that C0 goes to C0 is related to the condition that the diagonal goes to the diagonal in the period.
Exactly.
And exactly. Is there a version of this for Steinberg algebras?
Yes, there are several versions. I think that the most general is due to Steinberg himself. Yeah, so let me just briefly tell you about how this result is proven. So what Renaud did was to construct from a pair consisting of a C-star algebra and an abelian C-star subalgebra a groupoid that is known as the wild groupoid. And then Renaud showed that if you start with a topological principle, second countable locally compact Hausdorff et al. Groupoid, and you take its reduced C-star algebra, and as the abelian subalgebra take C0 of the set of units, and then from that pair construct the wild groupoid, you get a groupoid which is isomorphic to the original groupoid. And then it follows that if you have an isomorphism between the two reduced C-star algebra of the groupoids that maps C0 of the unit space onto the C of the unit space, then the corresponding wild groupoids are isomorphic, and therefore the original groupoids G1 and G2 are isomorphic. And that gives you 1 implies 2, and 2 implies 1 is straightforward. That's just follows from how the C-star algebras are constructed. But the wild groupoid is always topological principle. So there's no way of generalizing this result if you use the wild groupoid, because you can only recover topological principle groupoid in this sense here. But building on work I did with Brownell and Whittaker, Ruiz, Sims, Tomford, and I were able to modify this construction of the wild groupoid such that one can recover groupoids that are not necessarily topological principle. So, and in addition to that, we also generalized Renaud's construction by allowing the groupoids to be graded. So, if you have a groupoid G and a topological group gamma, then a map from G to gamma is called a cocycle if it's is compatible with taking the inverse and taking composition. And such a cocycle that will introduce a grading on the groupoid, and it will also induce a coaction on the groupoid C-star algebra.
Sorry, how does a cocycle differ from a groupoid homomorphism?
No, it's the same. It's just a when the homomorphism goes into a group, it's often called a cocycle, but it is just a homomorphism. So what I did with Lewis Simpson Tomford was to extend the construction of the Weil groupoid such that the extended Weil groupoid of a graded second countable locally compact Hausdorff italic groupoid satisfying the condition here that the interior of a certain subset is torsion-free and abelian in such a way that if we start out with a groupoid satisfying these conditions here, then this extended Weil groupoid is isomorphic to the original groupoid, and then it follows from that two topological groupoids satisfying these conditions here are topological isomorphic in a graded way, exactly when there's an isomorphism between their Cyst algebras that maps the zero of the unit space onto the zero of the unit space and intertwines the co-cycles, no, the coactions coming from the grading. So with this result here, you can actually prove all the results about the topological Markov shift and conjugate algebras, and also about the classical dynamical systems and cross products that I showed you today. Yeah, maybe just 2 minutes where I talk a little bit about the condition here. Mm-hmm. Well, first of all, maybe I will say that you're allowed to take gamma to be the trivial group. So in that case, the grading is just trivial. So that means that this result also covers the non-graded setting. So if you drop the grading on the groupoids and drop the coactions here, then the result still holds. Okay. Then let's look at this condition here. So again, like in the topological principle case, we are looking at the set of morphisms where the range matches with the source. And then in the graded case, we only have to look at the morphism that is trivially graded. And then before we ask this set here, that the interior of this set was equal to the set of units, or more precisely to the set of identity morphism. But in this theorem, we just ask that the interior is torsion-free and abelian. So what do I mean by torsion-free abelian? Well, it turns out that this set here, it's a subgroupoid, and it's actually a bundle of groups. And being torsion-free and abelian just means that each fiber in this bundle is torsion-free and abelian. And if the groupoid is a topological principle, then this is then all the fibers of the bundle is the trivial group, and so it satisfies this condition here. So it's a generalization of Reynolds results. You might ask, well, is this condition necessary here at all? Well, at least you need some condition, because if you take as your groupoid just the group, the cyclic group with 4 elements as one group, or one groupoid, and the other groupoid is the product of the cyclic group with 2 elements with itself, then you have 2 finite groups with 4 elements, and their Cyst algebras are isomorphic in a diagonal preserving way, but the groups, and therefore the groupoids, are not isomorphic. So when you have torsion, then this does not hold. So you need some kind of condition like this here, but it might be that you can relax this condition a bit here. And in the algebraic setting for Steinberg algebras, there are several versions of this result, and I think the most general one is due to Steinberg. And in the algebraic setting, you can even relax this condition and get something which is more general. But I don't know how to do it in the Cyst algebraic setting. Okay, I'll finish with that. So thank you very much for your attention.
Thank you very much for your wonderful talk. Yeah, so I wanted to ask, before I ask people to ask questions, I wanted to be sure to ask you something. You mentioned that in connection with the sister algebraic variant of Hassler's conjecture, that there was somebody's result who implied it in the particular case when the matrix was primitive. And I didn't fully catch the name. So can you say that?
Yeah, it's Ola Bradley and Kishimoto.
Brattelli. Yeah. Kishimoto. Okay.
Yeah. Yeah, I forgot the exact name of the paper, but
okay.
Yeah, they use a condition called what's it called? The Rockling property of the.
The Rockling property, yeah.
Yeah. I think it's more than 20 years old. This result.
Okay. So, are there any questions from the rest of the audience? I see there is one raised hand. Might it be mine? No. Yeah, it was mine. Okay, so, And do you know whether this isomorphism, equivalence between isomorphisms here and there, is there a K-theoretic leg that you could have a K-theoretic condition that these other equivalent conditions be equivalent to?
No, yeah, that's a very good question. That would be very nice, of course. So that, well, I guess, let's see. Well, for conjugate algebras, so how is it now? Yeah. So conjugate algebras, they are classified by their K theory.
Mm-hmm. Well, this is not simple ones, right?
Yeah. Well, actually, now there's for general conjugate algebras. Then you have to work with filtrated K theory when you have ideals. But yeah, let's just stick to the purely infinite simple case. But that's not the same as flow equivalent, and it's not the same as diagonal preserving isomorphism. There is this so flow equivalent. There is a algebraic invariant of that, and that's the K theory plus the sign of the determinant of I minus A. So there's a a difference.
So this would mean that the preserving the sign of the determinant is equivalent to asking that the diagonal goes to the diagonal.
Yeah. And that's at least to me surprising, and I don't know how to prove it directly, but you can prove it using cuboids, and that's actually what Matsumoto and Matsui did.
Mm-hmm.
They prove that the sign of the determinant is an invariant of the cuboid.
Mm-hmm. And so this. I mean, if it is an invariant of the groupoid, and you can recover the Leavitt algebra as the Steinberg algebra of the groupoid, then you also have the result for the Leavitt algebra. Something like that. I mean, it's also diagonal is also in the algebra case an invariant of the.
So whenever you have diagonal. In the diagonal case, then you get the groupoid, and when you have the groupoid, the C algebraic case and the Leavitt-Path algebraic case work the same way because you can use the groupoid to prove it. Yeah.
Okay. Go ahead.
Yeah. So when it's not diagonal preserving, you could not use the groupoid, and then I don't know what will happen if the Leavitt-Path algebra Steinberg algebra case is the same as the C algebra case. I don't know.
Well, what I was thinking is, we have this result that the purely infinite simple Leavitt-Path algebras of finite graphs that have the same K0 are homotopy equivalent.
Yeah.
And polynomially homotopy equivalent. So I wonder if perhaps perhaps it is true that if one has a homotopy equivalence that preserves the diagonal, then it must be an isomorphism or something like that.
That could be, yeah.
I see. All right. So let me see what happens. So are there going to be any other questions? Otherwise, I stop the recording and we can chat a bit. All right.